Hi guys, in this video we're going to be making a k-means clustering classifier from scratch using only Python, NumPy, and a few functions from the scikit-learn libraries. The purpose of this video is to really guide you step by step through the intuition and the math behind the k-means clustering model. If you don't know, the k-means classifier is a type of machine learning model that aims to separate data into different clusters of the amount which you specify. So this can be useful if you have a data set that you feel has different sorts of groups that it could be separated into. That would be a use case for this classifier. So this isn't intended to be something that you would actually use to process data. It's more meant to be a video on learning how this works, because obviously the instance of the classifier that we're going to code today is not going to be the most efficient nor optimized for real-world data sets. It's more meant for just learning the intuition behind the classifier. Okay, so we're going to be doing this tutorial in Google Colab. So as you can see, I already have a window open, and all the libraries that are needed for this model should be included in Google Colab. It's entirely free to use, and we can just create a new notebook. As you can see, I have a IPy notebook open here, and then we can just start coding. So the first thing that we're going to do is import the libraries that are needed. So we only need a few. So the very first library that we're going to import is obviously NumPy as np, and we're also going to import a few functions from scikit-learn. So from scikit-learn.datasets, we're going to import a function that's going to create fake data for us to test with. So this is the make blobs function. It's very powerful. It can generate fake data with the amount of samples, features, and the standard deviations that you want. You can also specify any centers, which is perfect for our model because that's how we're going to be differentiating the groups. And also we're going to import a few functions to measure our accuracy. So accuracy score. And we're also going to import a confusion matrix. This is going to help us compare our correct predictions with our incorrect predictions. And we're also going to import, let me just see my other screen here. We're going to import something to normalize our data. So from sklearn.preprocessing, we're going to import min-max scalar. I think that's the correct one. And also I think here we actually import this from metrics. So these are the libraries that we have to import. Oh yeah, and also we should import just the square root function because we're going to be using that. And these are the imports that we need. These should be everything. Actually, no, okay. We also have to import something to graph our results. So from, actually no, import matplotlib. So we're going to use that as well. So we're going to import matplotlib.pyplot as plt. That should just help us visualize our data if we're working with a two-dimensional data set. Okay, now this should be everything. And now we can start actually working on the classifier. Okay, now that we have the imports ready, we should be able to just start coding our actual model. So we're going to declare a class and call this k-means. And we're going to define the constructor function, so init, and here we're going to define which parameters we're going to take. So in order to start this model, we're going to take x, which is going to be our data set. This is going to be a NumPy array, and we're also going to specify k, which is just going to be an integer that tells us how many centers or clusters we're looking for inside our data. So we're going to declare a few instance variables as well, so we can access these in our other functions. So self.x is just going to be equal to x, self.k is just going to be equal to k, and we're also going to initialize a self.centers variable. So what this is, it's essentially a NumPy matrix which is of length k, and each row in that matrix has x different features. So it's going to be a k, and then the the columns of X is going to be the amount of columns in the matrix. So the shape of this is just going to be as follows. So we're going to use the random function to generate a few random values, and we're going to pass in, let me see, so self.k is going to be the amount of rows, right? And in order to get the number of columns that we should have, we're actually going to just pull out the columns of X. So if you don't already know, in NumPy you can get the shape of any matrix just by using the shape attribute. So x.shape could equal, I'm just going to use this as a comment, it could equal maybe 30, 40, and I don't know, 100. So this would be a matrix with 40 rows and 100 columns. So self.shape or x.shape is going to be a tuple where the second item in that tuple corresponds to the amount of columns we have. So if we want to access that for our dataset dynamically, because we don't know what our dataset's shape going to be ahead of time, we're just going to use x.shape, and then since it's the second number that we're looking for, we're going to pass in an index of 1. So indexes start at 0, so the first value would be x.shape of 0, so we're going to pull out x.shape of 1. And we're actually going to just use k here, just because the parameters are already defined. It makes our code look cleaner. So we have our centers initialized in the shape that they should be. Now we need to just initialize a self.classes variable. We're going to set this equal to none for now, but as we continue coding, this self.classes variable is going to just be a vector of length n, and each element in this vector, the ith element in this vector, is going to correspond to the class of the ith element in X. So what that essentially means is, suppose we have 3 samples in X and our self.classes vector looks like this. So we can have 0, 0, and 1. This is assuming we have 2 classes, 0 and 1. And a class just refers to the cluster or the group that we split the data in. What this tells us is that the first item in X belongs to the class of 0 or the group of 0. And so does the second item. Then the third item would tell us that the third item in X belongs to a class of 1. So this is just going to be a one-dimensional vector of length n, or let's say n is the amount of rows in X, the amount of features that we have. It's going to be a vector of length n for which each number corresponds to the corresponding sample in X, and the value of each index is going to correspond to the cluster that we're going to associate each sample in X with. So for now, we're going to leave this as none. And other than that, we're also going to declare self.n. This is just going to be helpful because we're going to be referencing the number of samples in X. So self.n, or I can also name this n samples to be a bit more verbose. N samples is just going to be x.shape, and this is going to be of 0 because we're taking the rows. It's assuming that the data is separated by rows. That's the shape that we want. And this is our construction function. Don't think we have anything left. Yeah, okay. This is all we really need. Okay, so now that we've defined the construction function for this model, we're now going to just define a few helper functions that are going to help us while we're processing our data. So the first one is probably the one that we're going to be using most often. We're going to just define a simple function to get the Euclidean distance between two NumPy vectors. So the way we do that, we're just going to define this as get Euclidean distance. And it's going to take in, well, self, and then v1 and v2, which are the two vectors. It doesn't matter which order we put them in because the distance is going to be absolute. So what we're going to return from this function is we're going to return, well, first of all, to find the Euclidean distance, we have to find the difference between these two vectors. It's like finding the distance between 2 points on a 2D plane. So we're going to subtract v1 from v2, and we're actually going to square this distance. So we have to square this, And this will give us a vector that has the element-wise difference of v1 and v2 squared. So what we're going to do with this vector that has the element-wise difference squared is we're actually just going to find the sum of this. Okay, so because we want a single value for Euclidean distance. Now, this is not, by the way, restricted to only 1, 2, or 3 dimensions. This will work in n dimensions because this is the generalized formula that we're using for any two vectors, provided that they're the same length. And with this sum, we're going to just take the square root of this because if you know the Pythagorean theorem, you have to take the square root after you find the distance between 2 points, regardless of how many dimensions that they're in or what the length of your vector is. And this is really it. That's the whole function. Seems a bit complicated, but it's actually very simple. And the second function that we're going to define is just going to be the normalization function. So this is not going to take any parameters other than self. And what this is essentially just going to do is it's going to just normalize our data. And let me see, so we're actually using the min-max scalar here. So let's just define m equals min-max scalar. And we're going to set self.x equal to m.fit transform. I don't know why I'm not getting auto completion here of self.x. Okay, so what this is going to do is it's going to take self.x and it's going to essentially express all the values in a standardized form. Instead of having extreme maximum and extreme minimum values, we want to have all of these values normalized so that we can correctly find the distance between these two vectors. So this is probably the first thing that we're going to do, even before we get to comparing the vectors and finding the closest centers to them. We want our data set to be normalized. So actually what we're going to do is after we initialize the centers, we're actually just going to call self.normalize in the init function. So since these functions are already going to be defined, this is going to normalize our data set before we even start working with it, which is going to be great. Okay, so these are the two functions that we're just going to use for utility. Other than that, we're going to define some more functions after this. Now that we have our initial functions defined, we're going to start with actually making the functions that will actually perform the machine learning calculations. So the first function that we're going to define is a function to find the closest center to a sample in the data set. So we're just going to name this find closest center. And it's going to take in self, obviously, and then a vector. And what this is essentially going to do is it's going to return the index in our self.centers array that corresponds with the most similar sample as this sample in the data set. So we're finding the minimum Euclidean distance of all of the centers. So we're going to try the get Euclidean distance function on all the centers, and we're going to see which one has the smallest distance. And also I see I've made a mistake here. I'm just going to fix that. I should probably run this and make sure that everything... Okay. Yeah, there's one mistake I made. I don't know where this is. Oh, just gotta do this. Okay, all the libraries. Oh, okay. Import min-max. Okay, I typed that wrong. We're just gotta make sure. Okay, looks like everything's good. Now we can continue. So to find the closest center, we're gonna define two variables to begin with. So we're gonna define closest center distance, and we're going to set this to be just infinity for now. So if you know in Python, infinity is defined as float and then just a string inf. So this is equal to infinity in Python. And we're also going to define closest center index. So this is going to be the actual distance, and this is going to be the index. So I'm going to set this equal to none for now, because I don't really want it to be a number, just to not cause any problems. And what we're going to do for I in range self.k. So k corresponds to the number of centers that we have, which is also the amount of rows in self.centers. So we're actually going to loop through every single one of these centers, and we're going to find the Euclidean distance between it and our data point, which is v. So how we're going to do that is for every single center in self.k, for in self.centers, we're going to set the Euclidean distance, so distance, or actually we're going to just get the center out first, so center equals self.centers of I, and we're going to set the distance equal to distance equals self.get Euclidean distance of center, or we can just pass in v, and then center. And then if distance is less than closest center distance, so that's why we have it set to infinity first, because, well, the first distance has to be less than infinity. We're gonna set, didn't type this in, so this should be closest. We're gonna set the closest center index. Don't know why I'm not yet. Closest center index is going to be equal to I, and after this loop is done running, we would have calculated the distance between every single center and v. So actually, this should be inside the loop. I don't know why I put this here. So yeah, center equals self.centers I. Actually, what am I doing? Yeah, this is the right one. I don't know why I was putting in the if statement. Okay, yeah, this is how it should be. Distance is the Euclidean distance between v and the center, and then center is going to be the actual element, the ith element inside this array. And then we're just going to return closest center index. And that should be our function. Okay, yeah, I think that is what I have in my notes here. All right, so that's the closest center index function. We're also going to define another function. This is going to be change centers, or actually no, that's not the one we define first. We're going to define map closest center. So what this function aims to do is it's going to go through every single data point inside of the X data set, and it's going to find the closest center to each of those data points. And then remember this self.classes array, well, it's going to set the self.classes of that index to the closest center. So we're actually going to store the closest center, or the class, inside the self.classes array after this method is called. So we're going to initialize a vector as an array. It doesn't have to be a NumPy array. And what we're going to do here is simply for I in range self.n samples, so n samples, this is the number of samples we have, self.x of I, we're going to find the closest center of that, and we're going to map the closest center index into our self.classes array. So we're going to call self.find closest center of our current sample, and we're just going to set the vector of index, or yeah, so the vector of I, sorry, not index, is going to be equal to index. And this is our function. That's really all we need to do. Okay, so now that we're done this function, we have one more thing left to do, which I forgot to put in the last section. We actually need to update the self.classes array with this vector as a NumPy array. So the way we're going to do that is simply by setting self.classes equal to a new NumPy array, and we're going to pass in a vector. And I think we might need to reshape this. Okay, actually, yeah. So we're going to reshape this into a column vector. So it's going to be a vector which has one column with n rows. So normally we would have this vector would only be a one-dimensional array with different values. But we actually want it in a shape that's kind of like this. So we want a two-dimensional array for which each element is an array that holds one value in and of itself. And this is just going to help for when we concatenate this to our final result. So we call this kind of like a column vector because it takes the shape of a column. So it's almost like a one-dimensional array, but each element inside it is an array itself. So the way we're going to do that, the way we're going to achieve that shape with this one-dimensional vector is we're just going to call the reshape function on this NumPy array, and we're going to pass -1 for the rows. So -1 as the first dimension length will essentially tell NumPy to infer the length of that dimension. And for the columns, we're going to pass 1 because we want one column again. And this should work. We should just set our classes to the shape that they should be. Okay, now we're done with this method. Now we need to add the last method to our class, which is the update centers method. So this is just going to change the location of the centers to the average location of the samples that belong to its class. So for example, the first center would be updated to the average location of every sample inside the cluster number 1. And the way we're going to do that is we're going to take the element-wise sum of every single sample, and we're going to find the average of that, and that is going to be the new location of the center. And we're going to do this iteratively until we can't find a better answer. So that's when the location of the center does not change anymore, or no new data points are added into the cluster, meaning that we've reached the best possible answer that we can get given our initial conditions. So the way we're going to code this method out is we're going to define a change centers function, and we're going to pass in self, and we're actually going to loop through every single class, so every single cluster that we have. So for actually no, we're going to loop through every single center that we have, not class. So for I in range self.k, because k is the length of the array of centers, so we're going to pass in k as the number of rows. So we're going to go through every single row in that matrix, and for each I, first we're going to pull out the center. So the center is just going to be self.centers of I. And what we're going to do now is we're going to actually pull out every single data point that currently belongs to this class. So every single data point that was previously mapped to its closest center, we're now going to separate those data points out by whichever center is the closest to them. And then we're going to recalculate the distance to that center using the new groups that we've just made. So the way we're only going to extract the data points that have a certain center I is using Boolean indexing. So the way we're going to do that is we're going to call self.x, and we're going to use square brackets to index it, and we're going to pass in an array of true and false values. So the way we generate that in NumPy is actually just by calling numpy.array, and we're going to pass in a Boolean expression. So this expression is going to be self.classes is equal to I. So wherever the self.classes array, remember the self.classes array is an array for which the element at index I signifies the group that the sample at index I belongs to. So if the third element in self.classes is 2, that means the third sample that we have in our self.x belongs to the cluster number 2. So we're only going to take the samples that have a class of I. So we're able to separate our data into different clusters. So this is going to return all of the samples that belong to that certain class. All right. And then we also have to, hold on, let me just look at my notes here. We also have to reshape this into a one-dimensional vector. So the way we're going to do that is just, once again, by the reshape function. And we're only going to pass in one parameter, -1. This just tells NumPy that we want a one-dimensional vector of any length. That's why we put in 1. So it's going to infer the length of that vector. And also, I think, oh yeah, so now that we have all these samples, we want to take the sum of them, an element-wise sum. So the way we do that is simply by taking this expression and calling the np.sum function, passing this in, and then the important thing that we need to do is pass in axis equals 0. So we're going to add up all these samples on the 0th axis. So that's just going to be the rows. Okay. Actually, I think I may have... Actually, no. What I need to do is I have to put this reshape in here, not outside of here, because if I were to reshape self.x into a one-dimensional vector, that would completely mess up our data. So you want to reshape the Boolean array that you're using for indexing, not the actual self.x. That was a mistake by me. Okay, now that we have all the samples in one cluster, what we now need to do is divide by the number of samples that belong to that cluster, because if you remember, we want to find the sum, the element-wise sum of all the members of this cluster, and then we're going to divide by the number of items in that cluster, because we want to find the average set of features for that one vector, which is the new location that our center is going to take. So the way we're going to do that is actually we're just going to divide by the length of this same array. So we can just copy and paste this and put that into our length function. And that's just going to return the length of the amount of samples, because once again, this represents the amount of samples that belongs to our class I, whichever one that may be. And if we just divide this entire sum expression by the length, we should get the average. So what this is going to be now, so self.centers of I. And in fact, I don't think we actually needed to put this here. Just erase that. But now we can actually divide this into a new line, just to make it look a bit cleaner. And we are going to set self.centers of I is now going to be equal to this new center. Okay? And we're going to do this for every single center inside K. And I think that's it for this function. Let me just double check my notes. And yeah, that should be it. Okay, yeah, this is pretty much everything for the change centers function. And now we should be getting on to actually testing this model and seeing if I did everything right. Okay, so now that we have all of our functions ready, let's just try and run this code once to see if we have any syntax errors or anything. Okay, so it does seem we have one. I don't think that it wants us to put this on a different line, so let's try running it without that. All right, that seemed to fix the issue. Okay, so I guess I have to keep this all on one line. All right, so now that we have essentially the main parts of the model done, let's write some boilerplate code to actually test our model with some fake data. So what we're gonna do for this is we're just gonna write if name equals main. We're going to create so first of all, km is gonna be a new k-means model. And actually before this, we need a training set and a k value. So we're going to initialize a training x and a training y. And this is going to be equal to the make blobs function. We're going to get 150 samples. They're going to have two features because we want to map them on a two-dimensional graph. The standard deviation is going to be, let's say 1.5 for now. And let's say that there are k centers. So let's initialize a k variable. Let's say k is equal to 2 for now. So we're going to have two different groups of distinct data points. And we're also going to pass that into the k-means model. Actually, first we need to pass in training x, and then we can pass in k if that's the correct order of parameters, right? So we have k and our training data. So what we're going to do now is we're going to just make a for loop. So we don't actually have the logic to stop changing the centers when we've reached the best possible outcome for our model. We can do that later on, perhaps in another video. I'm probably not going to cover that here, but for now we can just do a for loop of however many iterations we want. I think 50 would be reasonable. So for I in range 50, we're going to, well, okay, so we've already normalized our data. That's done in the init method. So all we really need to do is first map the closest center. So km.map closest center, and then we just need to change the center. So km.change centers, and that should, after being done 50 times, change the data in such a way that we can plot it on a graph neatly. So now, if we want the data, we can just pull that out. So the data is going to be km.x, but that's simply our features. We also want the y training data. We want the classes that it determines. So we want the actual groups that the classifier divides this data into. So the way we're going to do that is actually by concatenating this data with the self.classes. So we're going to have each sample is going to take a shape of a vector of length 3. So it's going to have some normalized decimal value. So it's going to have 2 values, once because 10 features. And then the third value, because we're going to concatenate these arrays, is going to be 1, 2, 3, 0, whichever class we put it in. We only have 2 centers, so 2 different clusters. So it's either going to be a 0 or a 1 in this context. So we're actually going to call np.concatenate km.x, and we're going to concatenate it with km.classes. And we're going to do this on the first axis. So axis equals 1. All right, so that means we're going to concatenate them horizontally and not vertically, because we want to add a column, not a row. So that's going to be the first axis, not the 0th one. So now that we have our data, we actually need to plot this on a matplotlib plot. So the way we can do that is, okay, well, we know that the item at, let's say, data point of 0 and data point of 1, these are your features. Okay, so these are your features. And then data point of 2, that's going to be the class. So remember, we had so each data point is a array of length 3, which has a decimal value, so something like that, and then a class. So we're going to plot these 2 values on the plot, and then this is going to correspond to the class. And in fact, I don't think we actually need to plot this in the beginning. We can do that later just to color code the points, but let's just work with these 2 data points for now. So how do we plot this? Well, what we can do is plt.plot, okay, and we're going to get data, and we're actually going to use NumPy array indexing. If you don't know how to do that, the first semicolon, we're not going to pass any arguments on the left or right. We're just going to pass a comma here. This is going to signify that we want every single row. And then here we're going to pass an array just with 0 in it. This is going to tell NumPy that we only want the first column, or the 0th column, in array indexing. We want to take that column and plot that as the, I guess, on the x-axis, all right? And then for the second argument, we're going to do the same thing. We're going to take all the columns of that data, but we're going to plot the second feature of that data. So we've plotted the 2 decimal point values. And then I think we can just pass in a color argument. Let's just say red. And I think that is what we want, right? Okay, yeah, that's what we want. All right. And we also need to plot the centers. We need to plot the center points, and we're going to do this after the data so it doesn't get covered up. We're going to plt.plot km.centers, and once again we're going to take every single row, and remember the centers have the same shape as the data, so we can just copy this shape over here and just replace data with km.centers. And we're going to plot this in a different color, let's say blue. So C equals B and C equals red, so this is going to be in red, and this is going to be in blue. All right, so let's do plt.show and actually show what we have. So I think I shouldn't have any syntax errors now. Let me try and run this. Let's see. Module object is not callable. Let's see, self.centers. What am I doing wrong here? So km equals k-means of training x. Self.centers equals np.random. Just give me 1 second. Okay, called the wrong function here. Just look at my notes. So it's actually np.random.rand. Okay, so that should fix this. Okay, so there's fit transform. Once again, min-max scalar has no, spelled that wrong. Okay, there's another error. Map closest center takes 0 positional arguments, but 1 was given. Okay, so that's because I did not pass self in here. So this is the debugging stage because we didn't actually run this model with any data yet. So we are going to get a few bugs here. Okay, local variable center was referenced before assignment. Where is this here? So map closest center, distance equals get Euclidean distance, v and center. Okay, so we need to actually just switch the order of these two lines around. So, right, that should fix this. Vec of 1 equals vec of I equals index. List assignment index out of range. I don't know why. Don't know, that shouldn't be an issue. With the vector of I equals index. Wait, let me see what I have here in my notes. Okay, so instead of doing this, we should just append this index. And hopefully concatenate got multiple arguments for axis. Okay, so when you concatenate these arrays, you just need to do this. So we want to pass a tuple for the 2 arguments. All right, these are, okay, wow. Okay, we use the wrong function here. plt.scatter, not plot. But this is a good sign. And it looks like we have our data points. All right. So I don't know why we only have 1 center showing up here. Let me try and print out. So it turns out that the bug as to why the centers were not showing up in the places that they should have been was because we're returning this function the wrong time. So it's just a issue with the indenting, and also we're not setting the distance to the new closest distance in this function. So after setting the index, we should also set the closest center distance to distance. Okay, that's just a little error here and there. Once again, all the source code is going to be linked in the description for reference. I know that there's a few things that I didn't do right the first time, but this should be working. Okay, let's run this code. And okay, I also changed the number of samples to 3 off screen, but let's just do this as 2 samples. Okay, so k equals 2. We should have 2 distinct clusters, and yes, the blue dot is the the average center. So this is the center that the model predicted, and it's dividing the data pretty evenly. So we have this blue dot here, and we can run this code again. Sometimes, especially if we turn the standard deviation up, the model is not that accurate. As you can see here, it's quite ambiguous in the middle. Like you can kind of see division in here, but as soon as we go higher than about 3, the predictions become pretty much incoherent. So once again, this is only in 2 dimensions. I'm going to turn the standard deviation down all the way to 1 now, so we get really, really distinct samples. And I'm just going to show you what can happen if we change the features to 10. So now that we have 10 features, our data, well, that was kind of lucky. I don't know why it's doing that. Okay, we shouldn't actually be getting accurate predictions now because we have 10 features that are now dependent on the data. So now the data is of length 10. Each data point is now of length 10. We have 10 different metrics that we can use to make predictions with. What we can do now actually is compare the training Y to the self.classes. So the way we're going to do that is we're actually going to print numpy.concatenate training Y and then km.classes. And we're going to do this on the, and I also need to put this in a tuple. And we're going to do this on the second or the first axis. And we're going to see, okay, what happened now? Axis out of bounds. Oh, training Y dot reshape -1 and 1, because we want this to be a 2-dimensional array, so we can concatenate this. Okay, so it kind of seems that we are getting a few of these samples are the same. As you can see, well, most of them here. Let's see if we can predict an accuracy score. Well, actually, that would be a bit difficult because the labels on the training data and the labels on the predicted data are not the same. Not because the model wasn't able to differentiate them into clusters, but because the labels are simply chosen at random. So there's no real way to predict the accuracy score. What we can do is use the confusion matrix and pass in the training Y, and then km.classes, and we're actually going to reshape this into a 1-dimensional vector. And let's see what this prints out. Okay. Oh, wait, why are we only getting... Oh, yeah, because we only have K. So it seems that even with 10 features, it's distinctly organizing them into 2 groups, which is what should be expected because we have 2 K values. Let's try 4 groups. And yeah, it's distinctly organizing the data into 4 groups. This is, of course, because we have the standard deviation only down to 1. If we increase this to 2, I bet we're going to get a higher error rate. Oh, actually, no. Okay, so it's still dividing the data into 4 groups pretty accurately. I mean, there's no predictions that are out of the classes, of course. Okay, maybe it's because we have 10 features to work with and quite a bit of samples. If we were to just try like 50 samples and also turn the standard deviation up a bit, and let's see. Okay, so we're still not getting any incorrect predictions, and I'm worried that there's some overfitting or something going on because we should probably not be getting this. Okay. Or am I even passing the right data into the confusion matrix? Okay, well, all right. Let me try using 5 features because we should have still some incorrect predictions. Okay, now we have a few that are not, that the model is not too sure of. So as you can see, it's being put in the same column or row. That means that 2 points that should have been in the same class, or this is the, well, in a 4-dimensional confusion matrix, these are the well, in a 2-dimensional one, you'd call these false positives. let's just say that these are ambiguous cases that the model is not sure of. So we can turn this all the way down to up to 5. And let's increase the number of features to something bigger so we have more data to work with. Okay, so now there's a lot of data points that the model is still unsure of. So this is kind of how we measure the accuracy. And the graph doesn't mean anything because 5 features is far too much to plot on a 2-dimensional plane. So for this, you probably don't even want to graph it. It's useless because we're only working with the first 2 features when we graph. And once again, there's one sample that is an ambiguous case. This is with a standard deviation of 2 and 500 samples. So yeah, this is the k-means clustering model. You can play around with the training data. Again, this isn't optimized for pretty much anything, but this is a working machine learning model made entirely from scratch. So if you want to download the source code for this, of course it's going to be on my GitHub. If for some reason you weren't able to get this working on your own, just try and look over the code once again. I tried my best to explain the design patterns and the reasons behind all of these functions. And once again, you can just look at this code in Google Colab. I think I'll also link this in the description if I can. And you should be able to just play around with these parameters and see what type of results you get with this makeshift machine learning model. Okay, thanks for watching. Make sure to leave a comment or a like, and I'll hope to make new videos next time.